Okay, so this is the last fourth and final lecture in this series on Witt vectors. Before we start, I just had a few questions. Actually, yeah. Uh, so I just wanted to firstly, I just wanted to confirm. So you said that there are three different rings: Wn diff of Fp, Z mod p to the n plus one, Z, and Fpt mod t to the n plus one.
Okay, yeah, let me write these down. So, okay, so questions. Okay, so what did you have? W, which one was the first?
Wn diff Fp.
Okay.
Z mod p to the n plus 1 Z.
Yeah.
And Fpt mod t to the n plus 1.
Yeah.
So just to confirm, so you're saying that the first one is not isomorphic to either of the other two?
Yeah, I guess these two will be isomorphic if n is smaller than p or something like that.
Okay, so if n is smaller than p, then these are isomorphic. And this is very interesting for us because we've been so far trying to compare just SLN over the latter two.
Yeah.
And we haven't at all, like, even, but this Wn diff, it isn't so intimidating somehow. It's right. I mean, it's yeah. So
no, absolutely. And maybe in some respects, maybe it's even nicer than this one. Like, I mean, I think they're about equally nice, but in some respects, maybe one is a little nicer and the other one's a little nicer.
But they're both local rings.
Yeah.
Of length n or n plus 1 or yeah, with the same residue field. So somehow it's very strange that one doesn't. Are there any more? I mean, can we understand all these things?
I don't know. There's something called divided powers in divided power algebras.
Yeah, isn't that Wn diff?
Yeah, well, exactly. So this one basically has divided powers on it, but then I think there are kind of partial divided powers. So you might have things like, I don't really know, but because what ord p of n factorial is,
right.
Whatever it is, like, what is it? Something like this. And so in effect, if you have divided powers, really all you need is expressions like this, where this question mark is this thing here. And I think you can even have partial divided powers, like they form a reasonable theories where at one extreme you have this, which is the full divided powers. At the other extreme, you don't have any denominators, but in the middle, you could have something like, I don't know, p to something small.
I see. Oh.
And then maybe there would correspond. Maybe there's a kind of a theory in between. I really don't know.
Okay, it's intriguing. I really find this very fascinating. In combinatorics, we kind of try to also understand, there's this ordinary generating function to exponential generating function transformation, but it doesn't preserve multiplication, right? So, you have a series and you try to transform its ordinary generating function to an exponential generating function.
But Jim, I'm confused. I thought there were only two local rings, or complete local rings with residue field Fp.
No, you have polynomials in 12 variables, power series in 12 variables. But you're talking about something, you need some other condition to rule out higher dimensions.
Yeah.
I mean, in some sense, this would be, I think this one would be something like, you know, say I don't know, I'm just going to guess. I think this would be something like, let's see, maybe t to the p, and then maybe direct sum, just this. So this, I think this is kind of another parameter. So it's kind of a little bit of a two-dimensional local, like, so maybe maybe this is something like fp adjoin t comma u modulo t to the p u squared and tu, or something like this.
Oh, it's not a principal ideal.
Yeah.
That's the hypothesis you forgot.
Yeah, I guess that's right.
Okay.
I really, I haven't really thought about, I only kind of made up this construction here because it was useful in the exposition of these lectures, not because I've ever thought about these objects.
Somehow I got obsessed with it. So.
Yeah. I mean,
it's easier to understand. So.
Yeah, of course. I mean, one thing, so the nice thing is, of course, these are related to derivations. And you can ask what this one is related to, and the concept of this so-called Hasse-Schmidt, I can't remember if I mentioned this, derivations. And this is a whole system of operators that looks formally like this. But it's not just a single operator, which is why I chose to go with this one in the exposition, because there's just one derivation, similar to the Witt vector case. So the Witt vector ring is a little more complicated. But on this side here, the derivations are a little more complicated, but the Witt vector ring is simpler. So I thought it was expositorily better to go with this one.
The one on the left has a lot of, I mean, it's something familiar to people in combinatorics, and because it refers to exponential. And surprisingly, Joyal actually did a lot of work on exponential generating functions. So.
Yeah, he's an amazing guy. He kind of has his fingers in many different things. Always.
Yeah, I knew him from his work on species.
Yeah, exactly. Yeah. So. And also, he does in the infinity category stuff. All came from him. I mean.
So yeah,
I think Pooja had another question, right?
Yes, I wanted to ask one thing. So if so last time you talked about the Z mod P square Z and FPT mod T square, and the Witt rings are isomorphic for these rings. Now, if I have these, if Witt rings are isomorphic, can I say their nth truncation, the Wn of that ring, those will be also isomorphic or not?
Yeah, I think so. Yeah. But maybe we need n to be at least 1.
So that's where I'm kind of exactly.
You're going, yeah. That's what you're asking about, right? So
yes, W0 is not isomorphic. So
yeah. What's your question? Where in the argument do you use that?
I mean, I'm just asking that what, I mean, if the Witt rings, we know the Witt rings of these things are isomorphic, right? For Z and FPT mod T square. And so then I was wondering what, like at level n, what can we say about the isomorphism or not isomorphism?
No, I think it's true at any n. I mean, any n as long as it's not 0.
You're saying n greater than equal to 1, these will be isomorphic?
Yeah, I think so. I think they're both isomorphic to Wn of Fp direct sum a product from 1 to n copies of Fp, and this is a square 0 ideal. And I think that, and why does it fail for Yeah, I think I think they're both isomorphic to this, but now I'm obviously it's not true when n is 0, and I'm trying to visualize the argument, and I don't see where that condition is required. But I will talk about this a little bit today, so maybe on this particular question, we could kind of wait and see how that goes in the lecture, and then we'll see more details. Oh, I think it's not split. So I think in general, for these two rings, you definitely have maps like this. And then you have a kernel, which I think will just be this. But the question is there a splitting? And I think maybe there won't be a splitting. Yeah, if n is 0, then there's not a splitting. But if n is 1, there is a splitting, I think. Yeah, so I think this is true for all n, but the splitting exists if and only if n is not 0. So these are things I would have to check.
Okay.
Okay, are there any other questions?
Yeah, anyone else maybe in the audience?
Oops. Okay, should I just get started then?
Yeah, I guess so.
Okay. Yeah, you're also welcome to interrupt me if you do have questions. This stuff is it's a little just a little confusing the first time you see it. Okay, so just to review, what did we do last time? So I defined the truncated vector rings, which are just truncations of the infinite one, and the ring operations are perfectly well defined. You don't need the higher components to define the ring operations on the lower components. And then I proved that there's an isomorphism like this, in fact, a unique isomorphism. And then the definition of the arithmetic jet space is that the R points, the points of this thing with coordinates in R, so to speak, are the same as the original variety, but with coordinates in the Witt vectors of R. And this should be compared with the classical geometric jet space, which is defined in the same way with these truncated power series. And one thinks of this scheme theoretically as arcs of order n on X. So a point on the jet space is an infinitesimal arc of points on the original variety. Because of course, right, this is the homomorphisms from spec RT mod t to the n plus 1 to X. Maybe I should say that's that one. So this, you think of this as a little germ of arc on X. And so this should be thought, the arithmetic jet space should be thought of as similarly, but somehow these are now arithmetic arcs, whatever that means. It's just Witt vectors, but okay. And then if you have an affine variety spectrum of a ring, then its arithmetic jet space is affine, and you can even say what it's the spectrum of, and it's this funny something like it's the nth piece of the free differential ring generated by A, the free delta ring generated by A. That's this construction that I told you about last time, which we won't talk about this time. But we will talk about this a lot. But we won't talk about this, so you don't need to worry about that so much. And then last time we computed the, just explicitly in coordinates, the first jet space of SL2 over the integers, the group scheme SL2 over the integers. And this is an algebraic group of dimension 6. So 6 because SL2 has dimension 3. And then J1 adds 1 level. So 3 more dimensions, the original 3. And we get 6 over Z. And in fact, it's smooth. It's sort of a general fact, which is quite easy to prove, that if you take an arithmetic jet space of something that's smooth, the result will be smooth. And then we also computed the fiber over P of this algebraic group. And this algebraic group, so this is an algebraic group over Z. So you can reduce the defining equations modulo P, and you get a new algebraic group in characteristic P. And it's an extension of the original SL2, but now by a 3-dimensional affine space, which is in canonical bijection to the Lie algebra of SL2. So it's just has it's just a commutative algebraic group of dimension 3. So this is an extension. So later today, I'll say what this looks like away from P. So this is the fiber over P. The fibers away from P are in fact totally split. It's just the product of 2 copies of SL2. So one way of saying that is that this big thing is generically it's a product of 2 copies of SL2, but degenerates over P to an extension of SL2 by its Lie algebra. So that's kind of, it's a little bit of a funny thing, but not too ridiculous. Okay, so what I want to go towards today is how to compute the Lie algebra of this thing, or for say Jn of SL2. How might you do that? And so the Lie algebra is in the theory of group schemes, it's defined to be the kernel of. So you have our algebraic group Jn of G. You can base change to any larger base you like, and that's what this denotes. And its Lie algebra will be a vector space over K, and it's exactly the kernel of this right here. This, if you like, is the K points of the tangent bundle of Jn of K, mapping to the original group. So it's just the fiber over the origin of that. And it's a little funny that this itself is also kind of a geometric jet space construction. In some sense, though, that will have nothing to do with the JNs I'm talking about. No doubt, if you kind of looked into all this in a much deeper way, the fact that this is some kind of jet space construction, and so is this, would be important. But in this lecture, it doesn't. It won't be. But so this one is just by the defining property of Jn. It's just the points on G with coordinates in now the Witt vectors of these dual numbers. So this is what Pooja was asking about, things like this. So how might you understand that? So you have this, and then if you can just mod out by epsilon in the entries of all the Witt vectors, and then you get. So imagine G is SL2. You get a matrix with entries in Wn of K, and the kernel of that map is exactly the Lie algebra of Jn of K. But to understand this, we have this question: how do we compute in this crazy ring? And that's going to kind of be, so what the whole lecture is going to be about is kind of how to do this computations, and then at the end I'll tie it up with getting back to the Lie algebra just to kind of illustrate it. Okay, so are there any questions on any of that? Oh, lose it. No, I don't want to get there. Yeah, okay. So now I have my notes here. Okay, so what we need to talk about first is the so-called ghost components, which you might have heard of in usual bit vector theory. If you're going to do any computation, basically you have to go through the ghost components. Okay, so what's the point? So recall that the ring structure on W of A, as I defined it, is given by the Leibniz rules for the nth iterates of delta. And these are complicated. Like you can't even write them down in closed form after n equals 1. But the only important thing was that these things were the generators of delta. So remember that we had delta is generated by all these iterates of. I mean, in fact, the way I defined it, it was just freely generated by definition by these symbols. But then I made the point that it's also possible to choose other generators, and you get a different set of coordinates on the Witt vectors. And some coordinates might be better for some purposes, other coordinates are better for other purposes. So we can ask ourselves the question: can we find generators with simpler Leibniz? So if you choose different generators, then the ring structure with respect to the coordinates induced by those generators will be given by the Leibniz rules for the new generators. So if we want a simpler way of thinking about Witt vectors, we can ask, are there generators with simpler Leibniz rules? The answer is yes and no. So I'll tell you we'll consider the iterates of phi in delta. So remember, so the 0th iterate of phi, sometimes I call that just the identity operator, or the 0th iterate of delta. The first iterate of phi was just phi itself, which is the identity operator to the p plus p times delta, and so on. So these things have two pluses, one plus and one minus. So the first plus is so you can think of these as operations. They're just on a delta ring. It's just the nth iterate of the Frobenius operation. The Frobenius operation is a ring endomorphism. So any iterate of a ring endomorphism would be a ring endomorphism. So they act as ring endomorphisms on delta rings. So the Leibniz rules are simple. You would what that would unpack to is if you made kind of Witt vectors using these coordinates, then addition and multiplication would just be given component wise. The simplest thing you could imagine. But the problem is that they actually don't. They don't generate delta. So for instance, if we mod out by p, so delta over fp, then right, this Frobenius map here, modulo p, it's just the pth power of the generator we started. So then so phi 0, phi 1, and so on, all lie in FPE. And so this thing has infinitely many variables, and they only generate something of transcendence degree 1. But, however, they do freely generate delta if you invert P. However, delta adjoin 1 on P is freely generated by phi composed with n as z adjoin 1 on P up. Okay, so let me say what this means. Okay, so we have an algebra on a polynomial algebra on infinitely many generators. And this, what I just explained. So these are not so. This is not so hard to prove. In fact, I think I mentioned it earlier. You just prove it by induction. It's really not hard. The point is that if P is invertible, kind of knowing phi and delta are equivalent information. So you can just go back and forth between them because you can divide by P. So you prove it by induction. You can stop at, say, order 2, like I've written here in with the first 3 variables. So it's even true at all finite levels as well. So that you just prove it by induction. When you add one more phi composed with itself n times, it's the same as adding the nth iterative delta, as long as you can divide by P. Right, so this is, so in particular, they're algebraically independent. And so we have an injective homomorphism here, and it induces an isomorphism if you invert P. So this is what we call delta. And now let me call this capital Phi. And this now we can look at the functors. The homs from delta is the Witt vector functor, right? So this gives a map. We have ring homomorphisms from delta to a general ring A, then maps to ring homomorphisms from phi to a general ring A, just by precomposition. And then this, remember, was kind of our conceptual way of thinking about the Witt vectors, where these free generators map to in A gives exactly the components of W of A. And similarly, this is identified, let me write it this way now, with an infinite product of copies of A. So should I say how it goes? So like if you have a homomorphism alpha, it goes to the vector, and I'll use angle brackets here, and you'll see why in a minute, where it's at the nth component, it's just alpha evaluated at that symbol. So it's just, and this one, just for completeness, let me write that up. This is just vector where at the nth component, it's alpha evaluated at that symbol. So this defines a homomorphism here, which we'll call little w now. And this is the ghost map. So W, the ghost map. Okay. So now the point is this. This is a ring homomorphism if the target has the product ring structure. So component-wise operation. Okay. I should probably say why that's true, but in some sense, the answer is almost a tautology. In fact, everything is set up in such a way that in fact, the way you could view the ring structure on W of A as being defined in such a way that forces this to be a ring homomorphism. That's another way of looking at it. So let me just give you a little bit of an argument, so you can some of these things are well, many things are formal, but still quite helpful to kind of see right now. So I'll say this is true essentially by definition. So okay, so what do I mean? So let's think about addition. I'll prove it's a group homomorphism. So addition, remember, the additive structure on the Witt vectors was defined using the Leibniz rules for addition of the delta operators. So let me talk about those Leibniz rules in a slightly different way. Okay, I'll write up a diagram, and you might have to just wait a second to understand everything about it. Okay, so what I claim is right, phi is what we talked about above. Phi is a subring of delta, and if you invert p, then phi and delta become the same. So delta, because delta is p torsion free, I guess, delta can be viewed as a subring of phi adjoined 1 on p. Now, what are these horizontal maps? These are the Leibniz rules for addition thought of as ring homomorphisms. So what do I mean? I mean, so here's what you do. You take the ith generator and you just send it to this, which is kind of formally meant to encode the fact that phi composed with I times of x plus y is equal to phi I of x times 1 plus 1 times phi composed with I of y. So when I talked about Leibniz rules, I could have talked about them as co-operations like this. I didn't really emphasize that point of view, but that's something you can do. And then the point is that this map here, there exists a unique map there making that diagram commute. Sorry, the top map is kind of defined by the same rules as the bottom map. It's just the extension of scalars if you invert p. And for instance, this top map would send the generator delta to delta tensor 1 plus 1 tensor delta minus the sum of 1 on p choose I, e to the I tensor e to the p minus I. So, right, this is kind of a co-product way of saying these are just two kind of ways of saying the same thing. So maybe if I wanted a more kind of formal approach to Leibniz rules and things like this, I would have talked about these co-operations. Okay, but then, but the addition structure on these Witt vectors is given by exactly this. So for instance, so we have W of A cross W of A goes to W of A. This is addition. From this point, you know, I told you that addition of Witt vectors was essentially just came from the Leibniz rules for the delta operators with respect to addition. And from this point of view, the way that works is this is hom from delta to A cross hom from delta to A, mapping to hom from delta to A. And what is this map? Well, this homomorphism, two homomorphisms from delta to A can be thought of as one homomorphism from delta tensor delta to A. Because if you like, the co-product in the category of commutative rings is just the tensor product. And then this map here, then this map, so plus is pre-composition with, let's call this Leibniz rule for addition with Leibniz rule for addition. So if you have a homomorphism from this into a ring A, you can pre-compose it with this and you get a new homomorphism from delta to A. So if you, in other words, if you have two homomorphisms from delta to A, if you can combine them going through this and you get a new homomorphism from delta to A, and that's exactly what, that's maybe just a more sophisticated way of saying the actual definition I gave for the ring structure on delta. But then the compatibility, then this thing up here is a ring homomorphism. Is the statement exactly that this square here is commutative. So if we have right, if you have a, okay, so it's why should this be an additive map? Oops. Why should this W be an additive map? Well, suppose you have two Witt vectors, so two things in here. That just means one homomorphism to some ring A. If you first add them, which means you first look at that composition, and then you apply the map, which means you look at that, you want that to be the same as first applying the map, which is doing this, and then adding them together. But that's just, both of these are, you're just pulling back this map the two ways around this commutative square. So they're the same thing. So maybe I'll just say, so the commutativity of star is equivalent to the map W being additive. And likewise for multiplicative, but now we need so multiplicative and the Leibniz rule for times. So the Leibniz rule for times would be, it's the exact same diagram, except this map would be different. It would be phi composed with I, tensor phi composed with I, because phi composed with I of a product, x times y, is the product of the two things, not the sum of the two things. So let me leave it at that. The point is that it's effectively just a formal fact. The way that it's a formal consequence of how I defined the ring structure on W of A. Okay, if it occurs to me, maybe I should mention, so this, I wrote a paper called Statistic Algebra. There's kind of a whole world here with Ben Wieland. It's in Advances Math, I think 2005, which kind of you know, if you in the usual world, you have you have groups, and then on commutative groups, abelian groups are wonderful things, and in fact they have operators which can act on them, and the systems of operators that can act on commutative groups are called rings. That's one way of kind of defining a ring, is that you can think of it as a kind of a system of operations that can act on an abelian group. And now on those, we can look at commutative rings. And the systems of operations that can act on commutative rings is some higher level of gadget. And so there are now, in it, a group acts on a set, it has only one operation. A ring acts on a commutative group, and it has two operations: the original composition, but also pointwise addition. And in our world, we're one level higher. So we have three operations. We have addition, multiplication, and then composition of operators. So this is one reason I think people have a hard time with these things is simply because kind of the language of algebra is, there's a chapter of algebra that most people aren't used to. And they just don't know kind of the world of algebra in which it lives. And it's kind of equivalent to a student having seen groups and actions of groups and abelian groups and so on, but somehow rings is just like a whole different level, and he can't. Somehow talking about. So what am I trying to say? I've told you a story without actually mentioning that third level of algebra, and the analogous thing would be telling a student about modules just in using explicit operators without ever actually talking about the concept of a ring. So if you kind of want the abstract setting in which it lives, then you might want to see this paper.
So I mean, this platistic algebra comes up in the theory of symmetric functions, right? I mean, that's something some of us here are familiar with. And then there are these rules for platism with a sum and platism with a product, which look very much like these.
Yeah, that's why we named it this.
So is it the same? Is that a special case of this, or is it something just analogous?
I can tell you with symmetric functions. So so we can say lambda is the algebra of symmetric functions in infinitely many variables. So by the fundamental theorem of symmetric functions, this is freely generated by the elementary symmetric functions, but in all variables. And then this is something that's exact. Okay, so then there are three operations on lambda. One is addition. Every ring is additive. Two is multiplication. Yeah, every ring has a multiplication. And three is composition or plethism. Some people call it plethism. So if you have two symmetric functions, you can compose them by you write them as in terms of the monomials. So formally E1 is x1 plus x2 plus dot dot dot. E2 is x1 x2 plus x1 x3 plus dot dot dot, so on. You take your symmetric function, write it in terms of the monomials, and then what you do is you substitute the monomials of G into the variables of F. So say F of first monomial of G, second monomial, and so on. And then this gives you a new symmetric function. So here's a good example. If you have power sums, so Pn is x1 to the n plus x2 to the n, and so on. Pm. Oh, actually, let's just leave it at that. Then, if you take f composed with Pn, what you do is you just take all these monomials of this function and now substitute them into the arguments of f, and then so it's just the same polynomial but with all the variables raised to the nth power. So maybe I can write it this way. This is equal to f of x1 to the n, x2 to the n. And it's also equal to p, the composition the other way is also true. Because what would that mean? That would mean you take all the monomials of f and substitute them in here. So you take each of the monomials and raise it to the nth power and then add them all together. But that's just the same thing as as changing all the arguments to the nth power. So yeah, if you've seen this notion of plethism, so plethism in terms of representation theory of finite groups, I'd have to be, I don't really remember how that works. You'd have to explain it to me again, symmetric groups and so on. But for symmetric functions, that's exactly this this thing. So like maybe another thing to say, if you, so E1 is the identity operator with respect to plethism. But you know, E2 composed with E2 will be some kind of slightly hard thing. It's equivalent to asking if you take the second exterior power of the second exterior power of a vector space, how do you express that as a polynomial in just the simple exterior powers of the vector space? So it's the same thing. So this delta. Yeah, so, okay. Then the, so lambda is so in this paper, we coined this term, a plethory, as are delta and psi. So these are, delta is something that a system of operators that knows how to act on a commutative ring. So is phi, and so is E. And then and so this is getting a bit off track, but an action of lambda on R is the same thing as a so-called lambda ring structure on R. So if you're familiar with algebraic K theory, there's some concept called a lambda ring. And
sorry to sidetrack you, but just to take this analogy a little further, what's the analog of delta in the lambda in this symmetric functions?
Lambda is analogous to delta.
No, but we have this operation lowercase delta.
Oh,
right?
okay.
Is that plethism with P to PK or?
Yeah. So delta. So actually, they're not just analogous. They're built out of each other. So delta is freely generated by a single operator, delta. But now lambda is generated by the set of delta p for p prime. And so here delta p is the symmetric function, which is the nope, that's the wrong way. So this is a symmetric function in variables x1, x2, and so on with integer coefficients. So so it's in lambda. And it turns out that lambda is generated by all of these plus a commutation relation with respect to plethism. So if you have two primes, there will be a relation that they satisfy. So if you look in actually Joyal's 1980s papers, so there's one which focuses on delta rings, and the second one is on lambda rings, and he talks about this there. So so in that sense, because of this, in fact, lambda can be built out of all these deltas. Let me maybe I'll write it this way. This is the delta operator for the prime 2. the delta, and then the delta, the ring delta for the prime 3, and then delta for the prime 5, and so on. So this ring of symmetric functions is kind of, it's the free lambda ring on one generator, and it's related to these delta rings. It kind of combines delta rings for all primes together. The key fact, okay, the key fact is that the Frobenius maps have to commute for different primes. So if you take this relation here and write it in terms of the deltas, one for the one prime, the other one for the other prime, you get this relation, and then you'll see exactly. This is some mess of a polynomial, but you can write it down explicitly. So, right. So the summary is that, so delta rings are about rings with a lift of the Frobenius map out of prime P. Lambda rings are about rings with a lift, with many lifts of different Frobenius maps. So there's a lift of Frobenius for every prime P, and they all commute with each other. And then you have to play a game to, if you have torsion, as we did in these lectures, but it's the same game. Yeah, so that's exactly the relation. And then it's kind of a miracle that this has anything at all to do with symmetric functions. So why, this kind of didn't, these delta rings didn't seem to have anything to do with symmetric functions. Why should that have anything to do with this lambda? But it's true. This lambda is kind of a, you might say the delta is a local theory. It involves only a single prime, and the lambda is a global theory. It involves all the primes.
Thank you. That's very illuminating. Thank you.
Okay. Yeah. Good. If you look at this paper that we wrote, I think that we kind of tried to make sense of those things. I would do some things differently now, but we're exactly confronting like what kind of algebra are we dealing with, and exactly this issue of like a single prime and many primes and symmetric functions. We try to tell a whole coherent story there. So I think you might find it helpful to at least look at. Okay. Are there any other questions on that? Okay, so let's just go back. So remember, we have a ghost map, and it maps to the product ring. So you can understand Witt vectors by at least something about them by looking at their images in this product ring and doing all computations there. But so the key point is that this map is injective if A is P torsion free, and it's bijective. So this is a ring homomorphism. It's bijective if P is invertible. So the game is if you have a computation, you want to do a Witt vectors, assuming as long as you're in the P torsion free setting, you can just take the image and here perform your computation here. Assuming it's a ring theoretic computation, that the result has to be still in the image because this is a ring by the general theory. So then it just becomes a matter of finding the pre-image of the result of the computation back in W of A. Okay, so here's a question, however. I mean, in some sense, we haven't answered anything because, so how do you compute W itself? I mean, if you don't know how to compute W, then you can't. This recipe won't work. So let me see. Maybe before I launch into that, since that will take a little bit of time, let me just make a few remarks about the consequences of what I said above for jet spaces. So consequences. So observe there's also a truncated version here. So truncations are also fine. So if we put an n here and an n here, and everything would work just as well. So what do we have? If you have a variety X and you look at the points with coordinates in a Witt vector, you can just look at the image under the ghost map, and this will give you points with coordinates in a product ring. But this is, of course, just by definition, the R points of the arithmetic jet space. And this is just the R points of the product ring, the product scheme. So we have a map here. So then, since R is a completely arbitrary ring, that implies that we get a map of schemes, of varieties. So map of schemes. Therefore, we have a map of schemes, which, I don't know, I guess I like to be cute. I call it the co-ghost map. So J of something at least is kind of approximately a product. And I guess the point is that if you invert P, then what if you base change these schemes to this ring? So these are schemes over Z. You base change to here, then in fact this becomes an isomorphism, simply because all the test algebras R will be algebras over this ring, and so they all have P is invertible in all of them. And this would then the map from Wn of R to this product ring will be an isomorphism, so therefore the induced map here will be a bijection. So this is an isomorphism. So we'll go from J and X right. So the theory, I mean, away from the prime P, the entire theory of these arithmetic jet spaces is utterly trivial. It's just a product. So for instance, I think that's what I told you in the beginning. So J1 of SL2, this is SL2 over Z, just to be clear. And then after you take the jet space, if you base change to this, it's canonically isomorphic to the product of two copies of SL2 over this. But recall, this was absolutely not true over P. So over P, it's completely false. We had this SL2 FP J1 SL2 FP SL2 FP. Okay, so that's just it's a completely general thing that these arithmetic jet spaces are just products of your variety. Your variety could be an algebraic group if you like, but then away from P, that's true, but then modulo P, they degenerate into something, I don't know, it's more, it's like this. Okay, so now I can tell you how to do some computations. So that was a little bit of a side, a little bit of a tangent. So that we had two tangents actually. First tangent was on symmetric functions, and then the second tangent was the consequences of the ghost map for jet spaces. Actually, maybe that tangent started here. So now let me get back to this question. How do you compute this ghost map? Because once you can compute the ghost map, then you can do any computation you want in the ghost ring on the right-hand side of the ghost map. So how do we compute W? And I think the easiest answer is to use the traditional Witt components. Traditional Witt components coming from the generators theta n. So recall that this, I asserted, I didn't actually prove it. To prove it, you need a slightly complicated argument, inductive argument using some subtle congruences. But these theta n operators freely generated delta, where the theta n's were defined recursively by the following condition. But what that means, if we just now think about, so remember we have hom delta A. That was another way of saying what bit vectors were. And then we have hom phi A. This is another way of saying just this product ring. If we use the coordinates on WA coming from these, then this map is described exactly by these polynomials. So let me just tell you what it is. So these, I should emphasize, these are theta coordinates, not the original delta coordinates that I used to introduce Witt vectors. But what does that Witt vector go to? It goes to exactly, you just change things around exactly by these are the so-called Witt polynomials. So I like to write it with angle brackets on the Witt on the ghost component side. So the first one is just A0. The next one is A0 to the P plus PA1. The next one is A0 to the P squared plus PA1 to the P plus P squared A2, and so on. So this is somehow, it's exactly the map induced by those equations. If you like, the thetas are the coordinates on the left-hand side, the phis are the coordinates on the right-hand side. This equality here induces that map. Okay, and you can see some things that if you know these are called the ghost components. The ghost components of the original Witt vector. If you know the ghost components, to recover the, how do you recover the Witt components or the theta coordinates? Well, A0 you can recover from the first one. To recover A1, you can do it from here. You can just solve for A1, but you have to divide by P. And likewise, to recover A2, you can recover it then from this one, but then you have to divide by P squared. And so that's exactly why, if P is invertible in A, this map is a bijection. And it basically the same argument shows that if P is not a zero divisor, then you can always recover A2 uniquely if you know it exists. So that proves that this map is injective if P is not a zero divisor. Okay, so now let me use this as an example to finally do a computation for you. What I want to do, because I want to do this Lie algebra business, I want to compute plus and times for two Witt vectors, x0 ... xn. And what I mean by this, I'm using funny English. I want to compute the sum and the product of these two Witt vectors. But okay, that would be a completely general formula. What I want to show you is if we assume that the x's live in a square zero ideal and the y's live in a square zero ideal, which is very close to Pooja's question, or it's a generalization of Pooja's question, how do we do the computation? So I want to compute this in the Witt vector ring of length n of, we might as well look in the universal case. So we might as well just join these all as variables, but we want each of them to be in a square zero ideal. So we mod out by that, the sum of this ideal and that ideal.
Can I ask one question,
Yes.
Jim, before we go to this? So in the previous thing where you have talked about this, you have given this map to us, right? Ghost components. So we are, I mean, Amri and I were trying to do was this, you last time in the lecture, you gave us the Witt ring of ZP, right? Where
Yes.
you gave this product ring and you gave this conditions, right? So in this case, the P is not, I mean, P is not invertible in ZP, but the map is injective. So we see that you have those components, right? You saw it.
Yes.
But then you are still able to give us further condition on the coordinates such that it became an isomorphism. So if P is not invertible,
Yep.
can that be always?
Yeah, I think it's hard to say what the image is. So yeah, so okay, good. Let's do it. So example, W of ZP mapping the product ring ZP as image. Maybe I'll change B0, B1, and so on, such that B n plus 1 is congruent to B n B to B n plus 1. So there's right. That's what we said last time, but in general, there's no simple description of the image other than the definition. So, well, I guess so. Who knows? Maybe someone could come up with one, but in general, there is no simple description of the image of the ghost map. However, there is, if the ring itself is a delta ring, and I gave you last time, I gave you a description. So one way of taking this approach for a general ring is you can always write any ring as a quotient of a delta ring. And so you can kind of use that to, and then you can give a simple description of the Witt vectors of that big delta ring mapping onto your original ring, and use that to access, and then use that to access the Witt vectors of your original ring.
Mm-hmm. Okay, thanks.
Okay, so in fact, this is pretty easy, but I think it's kind of an illustrative example. So you kind of see how you can make things work. So by the way, maybe one thing I should emphasize is that this really is the universal case, because this will give us a formula for doing it even Witt vectors in any ring is where the x's are in a square zero ideal and the y's are in a square zero ideal, simply because any such thing will be a specialization of the image under a ring homomorphism from this ring here, which is the universal example. So, and this is the whole point. This is we've lifted the characteristic 0, so we can do we'll use the injectivity of the ghost map to do our computation. Okay, so here's what we do. So since the ghost map is injective, I'll just view the Witt ring, the Witt vector ring, as a subring of the ghost component ring. So I'll just say this is equal to, slight abuse of notation, plus, so this is the image of this x, these x's under the ghost map. So we have that, and now we use the fact that all these x's are square zero. So this is right. This is taking place. This is in this infinite product of z dot dot modulo that ring there. It's the infinite product ring of this. So they're all square zero. So the ghost polynomials simplify enormously. So you get x0, px1, p squared x2, so on, up to that's the last one. We're doing length n, p to the n xn, and then the y's. And now the ring operations on the ghost ring are defined component-wise. So this is about as easy as it gets. We can factor the p's out. iPad problems. But then this is exactly by the same argument as we did to go from here to here. This is the image under the ghost map of x0 plus y0, comma x1 plus y1, comma xn plus yn. So in this simple setting, the sum of these Witt vectors is actually defined component-wise. So yeah, if you're, in fact, we only use that each of the elements was, each of the components are square zero. So if you're adding two Witt vectors together and all the components are square zero elements, then you can just add them naively. So naive sum if components are square. Okay, what about the product? We just do the same thing. So this, I'll do it a little faster this time. So this, the x's, px1, p squared x2, xn, y0, y1, yn. We multiply them together, x0, y0, but now p squared, x1, y1, so on up to p to the 2n, xn, yn. But now this is just the image under the ghost map of x0, y0, p x1, y1, and so on to p to the n, xn, yn. So if the components are square zero, then the product of two Witt vectors is not quite the most naive component-wise one, but it's somehow twisted by a power of p, depending on which component you're in. These, by the way, are all the theta components, the Witt components. So maybe I'll just write that. So the universality of this example implies that the same formulas hold over any ring, even p-tor, crucially, even rings which are not p-torsion free, if the x's and y's form square zero ideals. So Pujal's example of Wn, these two examples this is relevant to that. I mean, of course, it's just the Witt vector. It's not of the whole ring, but of the part where things are square zero. Okay. Let's see. Yeah. So what? Just thinking about. Yeah. So okay. So question. So these x's, right, are the Witt components. The Witt or theta components. Question: what about the delta components? So here's a fact, which I'm just gonna have to ask you to accept, that if up to square zero, up to the square zero business, the two components are actually the same. So in fact, theta n is congruent to the nth iterate of delta modulo the ideal, the square of the ideal of all of the deltas, or equivalently of the thetas. So therefore, all theta components are square zero if and only if all delta components are square zero. So, so in fact, the same formulas hold. So, and therefore, because of this, so and the components are the same, and therefore, in which case, maybe I'll say, in which case, the two systems of components agree. So therefore, the same formulas for delta coordinates. Again, only if the delta coordinates are square zero. So it's very restrictive. But it's exactly the generality we need to investigate Lie algebras and tangent spaces. So, okay, so I think then you should be able to show that, I guess, yeah, if n is at least one, hopefully, so hopefully I'm just going to say again what Pooja asked about, but Wn of E mod E squared Z is isomorphic to the Wn of Fp direct sum a sum of 0 to n of E squared Z Wn of Fp squared isomorphic to Wn of Fp direct sum, similar sum of I haven't made a mistake, those are isomorphic. Okay, there are only a few minutes left. Let me just give the Lie algebra discussion kind of quickly. Maybe I won't give every detail, but I think it's kind of a nice way of bringing these things together. So the Lie algebra of Jn SL2. So it'll be something a little funny because, of course, this algebraic group away from P is just a product. So away from P, it'll be just a product of n+1 copies of the Lie algebra of SL2. But something funny will happen modulo P. There'll be some big abelian part because we have this extension by the group underlying the Lie algebra. So how does this work? Okay. So we have Wn of, let me just work over the integers because that case actually determines everything. You can determine that this is an algebraic group over the integers. So if you want to know it's Lie algebra after you base change to something, it's enough to just know it's Lie algebra over the integers and then base change that Lie algebra. So we effectively have to do computations in this. That's what the Lie algebra of the jet space comes from. So we have this map is in fact split, so it's a surjection because on the level of rings, right? Z, this is an algebra over Z, and then there's a kernel, and you can think of this as just the bit vectors whose entries are all epsilon times something. So kernel is the set of bit vectors like that. Just leave it like that. So we might call this sort of convenient notation to just call this the bit vectors of this. This is not this is a non-unital ring now, but we can kind of abusively extend our notation to that, and so therefore Wn of this is a split extension of algebras, and this is a square zero ideal. Yeah, let's actually go right because the multiplication. Remember the multiplication. So this is a square zero ideal. The multiplication laws, if we go back, were these, but if all the x's and y's are in the same square zero ideal, then all these products here will all be zero. So and they all these components are in this just the one-dimensional square zero ideal of this very simple ring. So this setting is split. This exact sequence is split. We have this, and this is also a square zero ideal. So it's if you like, it's a module under this ring, and then you can just take a direct sum and view it as a square zero ideal, and then that gives you the ring structure on this. So when we so what is when we compute the Lie algebra? So the Lie algebra of J and G is I don't want to say it. So it's homomorphisms from the coordinate ring of G to the bit vectors of the dual numbers. And this, I'm sorry, which lift, let me put an asterisk here, the ones which lift the projection onto epsilon. So these are exactly the derivations from O of G into this module here. But this module, as we discussed above, the whole computation I gave, remember, it's a square zero. It's a square zero ideal, and the addition is given component-wise. So this is just the product, 0 to n of z epsilon. And so homomorphisms, so maybe I should write it this way, these are the homomorphisms from the differentials. Into there, and this is just a product of n copies of the homomorphisms of the differentials into Z, and this is just the usual Lie algebra. So this is just a product of n+1 copies of the Lie algebra of G. So okay, that's very trivial. It's very boring, but this is just these are as Z modules. We still have the question of what the bracket is. So, and we know that there has to be something non-trivial happening, because when we did our example of J1 of SL2 away from P, it's actually the product. It's the product Lie algebra, so it's the component-wise bracket. But modulo P, there is this big abelian part, so it can't be the simple product. And what I claim, so let me just say, since I'm out of time, I could rush through the computation, but I don't think that will help anyone. But I'll put it this way: the multiplication on Wn Z x0 ... modulo this discussed above. So the point, so the Lie algebra is, the bracket structure is given by some commutators, and if you just work it all out, what happens on okay, let's go back here. So the ring structure, if you multiply two things, at the first component, it's just the usual multiplication, but the higher components, you twist it by larger and larger powers of P. And if you just unpack that, what means that when you do these commutators, you get exactly the same thing for the Lie algebra. So this implies that as Lie algebras, the Lie algebra of J and of G is canonically isomorphic to the product of n copies. Let me say it this way. It's this, where if you have a Lie algebra G and a scalar lambda, this denotes G, but with bracket twisted by the scalar with bracket. So it's just lambda times the usual bracket. So then you can see that this is exactly consistent with everything we discussed. If P is invertible, twisting by this bracket, you can always untwist by it. So if P is invertible, then the Lie algebra of the nth jet space is just, as a Lie algebra, it's just a product of n+1 copies of the Lie algebra of G. If P is 0, if you're working in characteristic P, so for example, the Lie algebra of Jn of G over Fp, the first component, you have the original Lie algebra, and then you have n copies of the Lie algebra G with 0, the bracket being 0. So this is a big abelian part. So we're just reducing the usual situation. This is the situation I just discussed, modulo P. Okay, so the purpose of all that was, so yeah, so what's the conclusion? The conclusion is that G, if G is an algebraic group, you can view the Z mod P to the n points of G as the FP points of a higher dimensional algebraic group, which is this nth arithmetic jet space, and it's defined using bit vectors. And you can compute with these things, and so I just computed the Lie algebra of them. A second point is that basically all computations, even if you're interested only in characteristic P, they always have to go through characteristic 0. And the reason is that Witt vectors are defined in characteristic 0. They're defined using the concept, using the phrase Frobenius lift. And the word lift has implicit in it characteristic 0. So it's true that there's some properties are often nicer for Witt vectors in characteristic P, but usually the best way to prove them is to figure out what happens for all rings, and it will be maybe a messier statement, but your proof in characteristic P will have to go through some property in characteristic 0. Okay, the final thing I wanted to say, I have this conclusion slide, is that here is I wrote up some comparison of the different coordinate systems. So these are the theta ends, these are the delta ends, and these are the phi ends. And so let me just kind of review them. So in terms of the definition of Witt vectors, these, oh, sorry, I did it backwards. These are the delta ends, these are the theta. So in terms of the definition, to define the Witt vectors and have all the functorial algebraic properties, maybe I should call this conceptual definition, but the Bouyam-Joyau components, the delta components are nice, and the Gauss components are great in every respect, except they don't form a complete coordinate system. They only work well when P is invertible, which in some sense invalidates them. But this is the origin of these other things. Okay, so in terms of the definition, the delta components are better. To get the Witt vectors off the ground using these components, you have to prove some theorem, some little lemmas, which are not formal. The category theoretic properties are much clearer from this point of view. The Frobenius operator, usually called F in the theory of Witt vectors, that is really clearest from this point of view. It doesn't really have explicit formulas in either point of view here, but I don't know, maybe I'll give this one half of a check. The delta operator is very clear from this point of view. It's just a shift. From the traditional point of view, it's not clear at all. The Verschiebung operator, which I haven't really talked about, is very easy from the traditional point of view and not so simple to describe in the delta coordinates. What I did talk about today was the ghost map being in closed form. So I defined the ghost map abstractly, but to write it down as an explicit polynomial, you can't really do that using the delta coordinates, but you can do it using the theta coordinates. The Teichmüller elements I also didn't talk about today. They're easy to describe in all three coordinate systems. And then finally, whether the coordinate systems are complete, meaning they work for Witt vectors of every ring, it's only these two coordinates. The Gauss components, they're not in bijection to the Witt vectors unless P is invertible. Okay, so I'm already a few minutes over, so I'll just stop here. Thanks for your attendance. It's been a lot of fun.
Thanks, Jim. We really appreciate you taking the time and effort to give us these lectures. Let's all unmute and thank the speaker for the lectures. Of course, we can still take some questions if there are a few. I mean, there are perhaps quite a few, but maybe, at least from probably from me and Pooja, but maybe we'll ask them over time or maybe through Uri or something. But if others, if there are any quick questions for now. Good.
I have a question. We talked about it, Jim, but maybe you can say something. No, it's just the right place to say it. What about the jet and the Lie functors? And to what extent they commute?
Okay, my first thought is, so at the formally, right, if you take Lie of a scheme, you get a vector space. It's no longer a scheme. Of course, one can then regard it as an affine space of that's appropriate dimension. But still, wouldn't it be? I don't think it. I mean, because then you get, when you take Lie, if you get an abelian group scheme. So if you, but you want, maybe you review it. Okay, so that's a good. Maybe let me reinterpret your question. So how about this? Can Lie, J, and G. Oh wait, no, I just. Oh, okay. So I just answered my own question. Can't be. I was going to say be recovered from the G. Say as some Jn of the G. And I guess the answer is just by right here. The answer is yes. I mean, maybe what I think, for instance, if G is any smooth group scheme over Z, I think what I said would be fine. Probably even much more generally, but I haven't bothered to think about exactly what hypotheses you need. So let me just say, yes, that's exactly what we did above, but that's for the first part. But yeah, I think I kind of think the right answer to your question is no, as you stated it literally, but but this right here is the proper interpretation of your question, and the answer there is yes, just by this construction, by just take a product and keep twisting by powers of p.
So it can be recovered, but they're not isomorphic or.
No. Well, it's. I mean, I would say yeah. So this just is the product of. So if you know this Lie algebra, you can recover the Lie algebra of that by just performing this construction, right?
But it won't be equal to the jet of the Lie algebra. Jn of Lie G.
Yeah. I mean, I don't think so. Like, as I said, the first problem I have is that Lie G is technically a module, not a scheme. But okay, but then you make it. Suppose you make it a scheme.
Yeah.
But still, I guess the bracket. So then, but then it's a commutative group scheme. It's just an n-dimensional affine space. So then, at least so then the bracket that you on this will be trivial. Whereas it won't be on this, but maybe there's a more sophisticated way of recovering the bracket. Maybe you want to view this as a Lie algebra scheme.
Yeah, exactly. So you keep the structure, it's a Lie algebra scheme. Then
okay, that's a good question. So okay, so yeah, I don't know. So Jn of a Lie algebra scheme. Well, this will be, in particular, it's a group scheme, so it'll be some algebraic group plus extra structure from the bracket. Yeah, I've never thought about this. What is this? I have no idea. But maybe it's actually not. I agree. It's a natural question. Maybe one could say something. Okay, we can talk about this. You know what?
Okay.
Just knock on the wall.
Will do.
Any other questions?
So I guess there are no more questions. Thanks again, Jim. It's been wonderful.
It was a real pleasure. Thank you, everyone.
Yeah, thanks a lot.
We'll keep in touch.
Yes, absolutely. Yeah, I'm happy to entertain if anybody just has any questions, just send them or